Abrasive jet machining. And this is first of the three parts that are being produced on this particular topic. This is Dr. Gurraj Singh. The first talk is going to contain first of all a basic introduction to abrasive jet machining, followed by the details of the equipment that is used for construction of the setup. Then we would like to discuss about some of the properties and characteristics of these abrasives that are used in abrasive jet machining, the types of abrasives used, the functions of the nozzle, as well as the functions of the carrier gas. So all of these are going to be covered in this first part on abrasive jet machining. So it is very much clear that abrasive jet machining uses abrasive particles that are impinged onto the workpiece material, and they are made to collide with it at a very, very high velocity. So as a result of this high impingement velocity, these abrasive particles, they tend to chip off the metal from these specific zones where these particles are being targeted at. And as a result, due to the repetitive hitting of these abrasive particles, the metal gets removed and the machining takes place. And these abrasives are carried out or carried on using a carrier gas. So the carrier gas, it usually has a velocity as high as 150 to 300 meters per second. So the gas that is carrying the abrasives is at very high pressure. The high velocity stream of the abrasives is generated by converting the pressure energy of the carrier gas or the air to its kinetic energy, and hence a high velocity jet. So therefore it is basically the pressure energy of the gas that is converted into the kinetic energy, and that is eventually supplied to the abrasives. The nozzle, it directs the abrasive jet in a controlled manner onto the workpiece, and as a result, so the nozzle, it plays a very, very important role in directing the abrasive particles to the zone where the machining is being performed. And the high velocity particles remove the material by micro-cutting action. So we call it as micro-cutting, or this phenomena is also called as micro-chipping. And what happens is that you have a large amount of small brittle fractures, and a series of such fractures eventually lead to the material that is removed and the machining to take place. So this is a basic block diagram of an abrasive jet machining setup. It starts with a compressor, because in order to give pressure to air you need a compressor. Then you have a pressure gauge here that tells you the amount of pressure that's been reached. This is followed by a filter that is used to filter any impurities in the air or the gas. And this filtered air now heads off to the mixing chamber, which is the most important part of an AJM setup. And it is this mixing chamber where the gas as well as the abrasive particles, they get mixed together. And you have another pressure gauge in order to decide the pressure that you want to supply to the nozzle. And then you have a control valve. Before the gas and the abrasive mixture reaches the nozzle, it passes through a control valve that basically regulates the amount of this abrasive and gas mixture that reaches the nozzle. And through the nozzle, this mixture is then concentrated onto the workpiece where the machining needs to be done. So again, it is very much clear from this image, the block diagram, that the gas supply is supplied through a cylinder, or it can be supplied through a compressor depending upon the source of gas that you have. And this is followed by your filters and the pressure regulators. Then you have a powder supply and a mixture. So you have a vibrator here, and this vibrator, it shakes this mixing chamber, and this is where the mixing of the abrasives and the air takes place. Then you have a foot control valve that is used to control the supply of the mixture of these abrasives and the gas to the nozzle, and then through the nozzle you have the abrasive particles concentrated onto the zone where the machining needs to be done. And finally, you have an exhaust which is used to collect all these abrasive particles and the mixture of gases. So first of all, you have an air compressor, and the normal pressure that is being used here is in the range of 5 bars So you have a pressure in the range of 5 bars that is used in the carrier gas. And apart from air, you can also use gases like carbon dioxide or nitrogen, and they can be sourced from a gas cylinder instead of a compressor. So you generally do not use oxygen as a carrier gas, obviously because of certain reasons related to oxidation. Next, you have the pressure control regulator. So this is basically used to supply or used to obtain a desired working pressure. Next, you have a dryer. Now this dryer is basically used to remove any kind of moisture from this air. So you need dry air, because if there's any sort of moisture, you will have these small abrasive particles. When they are mixed in the mixing chamber, they'll absorb this moisture, or the moisture will absorb those abrasive particles, and they'll get agglomerated. So in order to prevent that agglomeration, you need completely dried air, and this is done using this dryer. Then you have a filter. So this is basically used to remove any particulate contaminants that may have passed through the dryer. So the dryer and the filter, they are basically used for purifying the air. Then you have the mixing chamber. So here you introduce the abrasive particles into the chamber through a metallic sieve. And the mass flow rate of abrasives, it can vary depending upon the type of process that you're performing, but it's generally in the range of 15 grams per minute. And it depends upon the amplitude of vibration of the sieve as well as its frequency. So this rate can be varied depending upon the material removal rate that you desire at the end of the workpiece. So next you have an electromagnetic on-off valve. So this valve is basically controlled using a foot pedal or a handheld lever, and this controls the supply of this mixture of abrasives and the gas to the nozzle. Then you have a nozzle, and this nozzle, it is basically used for concentrating the mixture of gas and abrasives onto the single point where you want the machining to be done, and it can be carried out at a velocity as high as 200 meters per second, where these small abrasives, they collide with the brittle workpiece, they result into small brittle fractures, and eventually lead to the microchipping of the small metal particles of the workpiece and perform the machining operation. Now, what are the desired abrasive properties? What properties does one desire from these abrasive particles? It's a very important thing to note down here, because if your abrasives do not have these desired properties, you will not be able to perform the machining operation at all. So the abrasive particles, they must contain sharp edges for easy micro-cutting action. So you need to have sharp edges in these abrasive particles in order to have a cutting action. Next, they should have irregular shape, but variation of size should be low. So the shapes should be random. So you have irregular shapes, but you should have least variation of size. So they should have the same range of size. For example, if you're having one abrasive, say like this, the other one, it can be of a random shape. The third one can be of another random shape. But you should not have an abrasive of this size or this size or this size mixed all together. You should have abrasives of the same size mixed together, and this would improve the final surface finish that we will achieve after the process is over. Then these abrasive grits must not contain metal particles, because they can block the pipeline through which you are supplying all the mixture to the nozzle. So it should not have any metal particles. Then it should have good flow characteristics. So obviously you're making your abrasives flow through thin pipelines at high pressure, so they should have good flow characteristics. They should have high hardness and should be rigid enough. So hardness and rigidity, these are again two very important properties that you desire from the abrasives, because they should not get crumbled into the parts when striking with the workpiece, right? So it is a very important property to have hardness as well as rigidity. And finally, the abrasives must not be wet, they should be cheap, and they should be readily available. So they should not be wet, they should be cheaply available, and they should be easily available. So after this, the next very important question is, what are the commonly used abrasive particles in these processes? So they are basically selected on the basis of the size or the surface finish or the material removal rate that is desired. So the most commonly used abrasives are alumina or aluminum oxide as well as silicon carbide. So these are the two most commonly used abrasive particles in abrasive jet machining. Why? Because both of them are readily as well as cheaply available. So they are readily as well as cheaply available, which makes them the most frequent choice as abrasive particles. So aluminum oxide, what is the purpose that it is used for? So it is generally used for cleaning, cutting and deburring purposes for moderate to hard materials. So aluminum oxide can be used on both moderate as well as hard materials. Silicon carbide. So silicon carbide is a bit harder when you compare it to aluminum oxide, and as a result it can be used for all the above purposes that have been mentioned in case of aluminum oxide, but they are suitable for very hard work materials. So since they are harder, they can be used on harder materials, but they have a drawback. The drawback is that they can shorten the nozzle life, because they'll strike the nozzle at such high velocity, they'll tend to reduce the nozzle life. The glass beads. So glass beads are used as abrasives as well, and it is mainly used for producing matte surfaces for reducing transparency. So this is usually seen on the frosted glasses. Then you have crushed glass. So it is used for heavy cleaning, matting and peening operations. And finally you have sodium bicarbonate or baking soda. So it is commonly used for light duty applications such as cleaning and cutting and on softer materials. In order to have machining on softer materials, you prefer sodium bicarbonate. In case you have moderate to hard materials, you'll prefer aluminum oxide, and in case of very hard materials, you'll prefer silicon carbide. And for glass operations, you can use crushed glass or glass beads. So these are some of the commonly used abrasive materials that are available to us at cheaper prices and ready availability. Now next up is, what are the functions of the nozzle now in the abrasive jet machining process? So first of all, the basic and the primary function of the nozzle is to deliver the high velocity jet. So this is what the nozzle is employed for. It has to supply the jet onto the cutting zone, and the pressure of this mixture, it remains very high from 15 to 20 bars, while the velocity, it can remain low. And when this mixture passes through the nozzle, the static enthalpy of the mixture is transformed into kinetic energy, and thus it imparts velocity to the jet. So this is the primary function of the nozzle. Secondly, it controls the jet diameter. Now the jet diameter is again a very important aspect here, because it will decide the type of machining that you're going to perform. It is going to finalize the material removal rates. Now whenever we talk about abrasive jet machining, you will always quantify all these parameters in terms of the material removal rate. So you have the MRR, which is going to be frequently used throughout the course on non-conventional machining methods, and it is this MRR, the level of this MRR, that is going to finalize the various parameters that are used in any manufacturing process. Thirdly, regulating the impingement angle. So again, apart from the velocity and the diameter, the impingement angle at which the nozzle is aligned onto the workpiece. For example, this is your workpiece. This is the angle at which the nozzle is aligned. So this is a 90-degree impingement. But there are cases where the nozzle can be aligned at this angle, which can be somewhere around 45, or it can be aligned at an angle of like 75 degrees. So what will happen? Your material removal rate will vary. So normally it influences material removal rate and accuracy of machining. So this is the most important aspect while considering your impingement angle. And the highest material removal rate, it can be obtained at the impingement angle of 70 to 80 degrees. So after rigorous research experiments, the researchers have chosen this domain, this range, as the most optimal one for obtaining the maximum material removal rate. Then, if I talk about the different types of nozzles, so your nozzles, they can either be round shaped nozzles or they can be rectangular shaped nozzles. This is decided on the basis of the slots that are there. So you have either round slots or rectangular slots. And then further, they are split into either the right angled nozzle or the straight edge nozzle. And secondly, the rectangular shaped nozzles are also either the rectangular nozzle or the straight edge nozzle. So for example, you have one circular or round right edged nozzle here, and you have a straight edged rectangular nozzle here. So you have one from each categories that is shown in both these images. And what is the material of the nozzle? So either your nozzle is made up of tungsten carbide or it is made up of sapphire. Most commonly, it has a life of nearly 300 hours for sapphire, while only 20 to 30 hours for tungsten carbide. So this is decided on the basis of the wear resistance that these materials possess. And the nozzle is made of either circular or rectangular cross section, that has already been discussed. And the increase in wear of the nozzle, the divergence of the jet stream, it also increases and results in more stray cutting. So as your nozzle gets worn out here at the outlet, the stream of jet that was flowing, it may become a bit divergent, and this will in turn affect the surface property of your workpiece. So your nozzle wear rate is again a very important aspect while considering abrasive jet machining. Then lastly, we have the functions of the carrier gas. So the carrier gas, it again performs many important functions. The first and the foremost is it accelerates the tiny abrasive particles. So this is the major function of the carrier gas, that it is used for supplying momentum and transfer it to the abrasive particles so that these particles can now hit the workpiece at a higher velocity and with a higher pressure. And the final pressure of the mixture, it depends on the mixing ratio, the carrier gas pressure before mixing, and also the momentum loss during the mixing process. Then it helps forming the abrasive jet. So a nozzle is used to convert the pressure energy of the gas abrasive mixture to the kinetic energy, and thus a high velocity jet is obtained. So it basically serves this purpose and carries the abrasives until it strikes the work surface for eroding the material. Thirdly, it blows away the eroded metal particles and the used grits from the machining zone. So this is again a very important application of the abrasive of the carrier gas, because when you are performing the machining operation, your metal particles, your abrasive particles, they may tend to get deposited or scattered onto the surface. But since you have a gas at a very high pressure flowing onto the surface, so it blows away these eroded metal particles as well as these grits from the machining zone, thus making it all clear. So these were the important aspects related to the various components that are used in abrasive jet setup. So we have your nozzles, we have the gas supply, we have the abrasive particles themselves that are used in abrasive jet machining. In the next lecture, which is the part 2, we will be discussing about the various parameters that are used and that eventually they can influence the MRR, which is the material removal rate. So that would be the topic for the next lecture. Thank you.